Welcome to the Destination Earth Core Service Platform. Eagle is a visual workflow builder for geospatial AI, running on Destination Earth. It's a training environment, built to pull in satellite imagery, pre-process it, train or run AI models on it, and export results, all by connecting nodes on a canvas. On the left, you have the node palette, organized into data sources, pre-processing, inference models, tools, and outputs. On the right is your workflow canvas. At the top, the standard controls: save, open, new, and run. In this tutorial, we'll build a complete change detection pipeline that compares two Sentinel-2 images of the same area, taken 6 years apart, and automatically identifies what has changed on the ground. We start by dragging the nodes we need. For change detection, we require 2 raster input nodes, one for the before image, one for the after image, 2 band selector nodes to handle pre-processing, and finally the change detection inference node. Let's configure the first raster input. Right-click the node and select Configure. The configuration panel opens. Eagle supports 2 input modes, single file or folder for batch processing. We'll use single file mode. The platform accepts all standard geospatial raster formats: GeoTIFF, ZAR, NetCDF, and zipped variants. We click Browse Server Files and navigate to our project folder. For our before image, we'll select the Sentinel-2 scene from 2019. Eagle automatically detects key metadata, the sensor type as Sentinel-2, and the ground resolution at 10 meters per pixel. This metadata is used downstream for compatibility checks and reporting. Once the image loads, Eagle performs an automatic Earth observation compliance audit. We see warnings here: no metadata value defined, the file isn't tiled, and it lacks internal overviews. These won't block our workflow, but they're best practices for cloud-optimized GeoTIFFs. The platform also extracts and displays the full technical profile, the Coordinate Reference System, EPSG, 32634, the dimensions, all 13 spectral bands, and the data type. Below that, the Data Advisor is one of Eagle's most useful features. It analyzes your input and tells you exactly which models in the platform are compatible with your data. For our Sentinel-2 imagery, we can see flood detection, burn scars, solar farm detection, and, what we need today, change detection are all available. Before running anything, we can preview our images directly in the browser. Here's the 2019 scene of the area: open fields, scattered buildings, agricultural plots. And here's the same location in 2025, visibly more development, denser built-up areas. The change is obvious to the human eye. Now we'll quantify it with AI. We can switch between true color, false color, vegetation, agriculture, and SWIR composites, useful for inspecting different land cover signatures. Now we wire the workflow together. We drag from the output port of the raster input to the input port of the band selector. We repeat the same process for the 2025 image and its band selector. Notice how the connection lines turn green. Eagle is confirming that the data types and schemas are compatible between connected nodes. In the band selector, we choose which spectral bands to feed into the model. For change detection, we want true color RGB, so we select B04, red, B03, green, and B02, blue. The order matters. Bands are stacked in the sequence shown. We do the same for the second band selector, ensuring both images use identical band combinations. Consistency is critical for change detection. Now we configure the inference node itself. Eagle has automatically identified which input is the before image and which is the after. It validates that both images are spatially aligned, share the same dimensions, and use compatible band selections. We give the run a meaningful name, in this case, change_detection_thermi_19 to 25, so our outputs are organized within the project folder. For more control, we open Advanced Parameters. Here we can tune 3 key settings. Change confidence controls the model's threshold. Lower values are more sensitive and detect subtle changes. Higher values are stricter and only flag major transformations. We'll set it to 145. Points per side governs spatial granularity. 32 gives us a good balance between speed and detail. Stability score filters out noisy or low confidence detections. We'll keep it at 0.95 for clean, reliable results. Everything is configured. We hit run. Eagle now executes the entire pipeline on the server side. We can watch the progress in real time: the detecting, Indicator shows the change detection model is working through both scenes, comparing patches, and identifying differences. Workflow completed. Eagle has identified 41 distinct change instances between 2019 and 2025 across our area of interest in Thermi. The results are saved automatically to the project's output directory, ready to be vectorized into GeoJSON polygons, exported, or used as input to another workflow. With the workflow complete, Eagle opens a comprehensive results panel. We have 4 interactive views: comparison, enhanced, instances, and report, plus downloadable outputs in multiple formats: the binary change mask, probability raster, instance segmentation, confidence scores, and high-resolution PNG visualizations of each view. Let's walk through what the model actually found. This is the split comparison view. On the left, the 2019 scene; on the right, the 2025 scene, with high confidence changes highlighted in red. The story is immediately clear. In 2019, this part of Thermi was a patchwork of agricultural plots and scattered rural buildings. By 2025, the same area has densified significantly: new residential blocks, new roads, infill development. This is textbook peri-urban sprawl, and Eagle has flagged the most prominent transformations. The enhanced view goes deeper. Eagle doesn't just give us a yes or no answer, it produces a full probability surface for every pixel. Top row, left to right. The earlier image, the later image, the binary change mask in red, and the probability heat map. Brighter pixels mean higher confidence that something changed. Bottom row breaks this down further. The confidence levels panel uses a traffic light system: red for high confidence above 0.7, orange above 0.4, yellow above 0.1. The high confidence only view filters out anything below 0.5, leaving us with the most reliable detections. The histogram on the right tells an interesting story. Notice the strongly bimodal distribution. Most pixels cluster near 0, meaning definitely no change, while a smaller but distinct cluster sits between 0.5 and 0.62, meaning definitely changed. Very few pixels fall in the ambiguous middle zone. This bimodality is exactly what we want to see. It means the model is making decisive, well-separated predictions rather than guessing. The maximum probability we observed was 0.619. That's why the high confidence count above 0.7 reads 0. Our scene contains real but moderate changes, not catastrophic transformations like a wildfire or a flood. The instance analysis view turns those raw pixels into discrete, countable objects. Eagle has segmented the change mask into 41 individual instances, each one a separate detected change event, color-coded for clarity. Top right, we see those same instances overlaid on a uniform confidence map. Bottom left, the score distribution. Most instances cluster around a 0.60 confidence score, with a mean of exactly 0.600. Bottom right, the top 10 instances ranked by confidence, with their pixel sizes labeled. The largest detection covers 334 pixels, at 10 meters Sentinel-2 resolution, that's roughly 3.3 hectares of changed land. This instance-level output is what makes the results actionable. Each polygon can be exported as GeoJSON, opened in QGIS, joined with cadastral data, or fed into a monitoring dashboard. Finally, the comprehensive report, 6 panels of quality metrics that tell us how trustworthy our detections are. The IOU predictions distribution shows a mean of 0.924, meaning the model's predicted segmentation masks align very closely with its own internal consistency checks. Anything above 0.9 here is excellent. Stability scores average 0.974. This measures how robust each detection is to small perturbations in the input. A score this high tells us the model isn't producing fragile, noise-sensitive predictions. The change confidence distribution is centered around -0.75. Don't let the negative sign confuse you. This is the model's internal logit score, where more negative values actually correspond to stronger, this region changed, signals in this particular framework. Area distribution shows that most detected changes are small, under 1000 pixels, with a long tail of larger detections. This matches what we'd expect from urban infill: many small construction sites, a few large developments. The confidence versus area scatter plot reveals that confidence is fairly consistent across detection sizes, no strong bias toward only flagging large or only flagging small changes. Bottom line, in the summary statistics, 41 total instances, 37,956 changed pixels in total. At Sentinel-2's 10-meter resolution, that translates to roughly 380 hectares of measurable change across the scene. From here, every output is one click away. Download the binary mask as GOTIFF for use in GIS software. Export the probability raster for further analysis. Pull the instance polygons as vectors. Or grab the PNGs for reports and presentations. Everything is automatically organized in the project folder, ready to be shared with stakeholders or pushed into a downstream workflow. Thank you for using Eagle.